Good about this. Chapter 25. And most of this stuff, as usual, it's all in the recorded lectures that you can watch. How many of you have watched this already? Yeah. And just to make sure, you watch these at an accelerated speed, right? You're not watching them normal time. Yeah. Put it at like 1.5, 1.75, and the speed's just about right. Okay. So that's kind of what you want. All the equations that are really important for this chapter, we're going to go through. And then we'll do an example of how to draw these kinds of diagrams. And I have some worksheets for you. This is kind of cool because you can actually use a ruler and draw this stuff out, and it all works. You can actually do measurements, and you'll see that it actually follows through. The physics works. So in chapter 25, they kind of throw a lot of stuff in here. And one of the first things they throw at you is this, n equals c over v. And we know what some of these variables are already. What is c? We've learned about c. It's a number. It's 3.00 times 10 to the 8th, and what does that represent? That's the speed of light. That's how fast light goes. Okay? And then v. What's v? From physics 1. Velocity. This is velocity. And what n is, it's something called the index of refraction. And that, in particular, is a measure of how much light bends when it goes from one medium into another. So when I shine light into a fish tank or something, the light actually bends. And that bending we can quantify using this. We usually combine this with something called Snell's law. One of my middle school science teachers was Mr. Snell. Not the same Snell. That guy knew all sorts of stuff about biology, didn't know any physics. So he was basically useless. So he became an administrator. That's what you do. Snell's law. N1 sine theta 1 equals N2 sine theta 2. And we need to draw a picture that goes along with that. N1, N2. And I'm going to draw a dotted line. That dotted line is normal to the interface that joins the two different substances. So maybe N1, this is air, and N2 is water. So I'm going to shine a light from air into water, maybe a piece of laser light. I shine it, and it hits right here. And I'm drawing a line that's normal. What does normal mean again? Doesn't mean it's weird. It actually has a meaning. We did it with flux as well, drawing normal lines. It's the other word for normal. What's this angle between this and this? 90 degrees. Normal means 90 degrees, or perpendicular. So I draw a perpendicular line, and I have light that comes in and hits at that point where it's perpendicular, and it's going to refract. It's not going to go straight. It's going to actually bend a little bit. So let me see if I can draw this. So if the light went straight, it would go like that red line, but it bends because it's entering something new. It's entering into water. We'll see if I can dig up a laser and I can show this to you maybe next class. But what we want to do is we want to take those n's, N1 and N2, that's what these are, the indices of refraction. And then we can compare them to each other using Snell's law, which depends on angles. And these angles that we're measuring are theta 1 and theta 2. Those angles are relative to that perpendicular, relative to the normal. So I don't do from the horizontal line, I do from the vertical line. Theta 1, theta 2. Those are the angles that I'm interested in. Okay. So I'm measuring how much this light bends relative to the normal or perpendicular one. N1 sine theta 1 equals N2 sine theta 2. And we use this all the time. They use this in medicine all the time for something called a critical angle to make total internal reflection happen. And that's covered a bit more in the lecture and in the textbook. Then the next thing we want to talk about is we want to talk about lenses and mirrors. And there are equations that work for lenses and mirrors so that we can do all sorts of useful things with them. First, we want to know the power of a lens. Power is equal to 1 over focal length, where the focal length is where you focus light shining through a lens. This is the power. Physics 1, do you remember what the units of power were? Or last unit, power? Is watts. In this, power is different. This is diopters. Or capital D. Power of a lens, 1 over the focal length. Anybody do photography? Into photography? This comes into play in photography if you do that kind of stuff. So power is 1 over a focal length, and the focal length is where light is focused from a lens. So if I draw a lens, let me draw a horizontal line, and I'm going to draw a lens on this horizontal line. This lens takes any light that you send in. So let's say I send in a bunch of light from one side. This is what we call a converging lens, so it's going to make all the light converge to one point. That point is called the focal point. And the focal point is maybe somewhere right around here. So if that's the focal point, then this yellow light that hits down here on the lens is going to get focused into that one point. The light that comes in and hits up here is going to get focused to that one point. The light that comes in and hits the lens down here is still going to be bent and going to be focused at that point. Light that comes in, all going to be focused to the focal point. And the focal point is a measurement. It is a distance from the lens to that focal point. Okay? So that's focal point. Works for lenses, works for mirrors. And what we usually want to do with this is we want to draw diagrams that let us take an object, stick it in front of a lens, and figure out where the image of that object is going to be. So we draw this central line. The central line has a name. Anybody remember what it is from the lecture? I was just watching the lecture this morning because I had to remind myself. Even though I'm an astronomer, so I should just know all this stuff off the top of my head, this is something called the optical axis. And I can take a lens and I can put it on the optical axis. What kind of lens do you want us to draw? What should we draw? Do you want a converging lens or a diverging lens? Diverging lens? Okay. So I'm going to draw a lens that's diverging, which instead of focusing light, makes light bend away from itself. So maybe let's go up here and let's draw what a diverging lens would do to a bunch of light. Diverging lens. Okay, so diverging lens, we're going to have focal points on both sides of the lens. And what we have happening with a diverging lens is light comes in. I'm going to draw those same light rays that are coming in. A diverging lens is going to make light diverge. So the converging made light focus to one point, made all the light focus down to here. With the diverging lens, it's not going to focus light here. What's it going to do? It's going to make light spread out. But it's going to make light spread out based on the focal length of the lens. It still has focal length. It still has a focal length right here. It has a focal length over here. But all the light that diverges is going to look like it's coming from this focal point. So what we do is we can take a straight edge, and I'll show you this on the whiteboard. We'll draw one of these diagrams. But I line up kind of straight edge from the focal point to where the ray is, and I draw the line that way. And then I line it up with the focal length, draw a line going away. And that's going to show you where all that light goes. So the light looks like it's coming from this focal point and goes straight and diverges. Light looks like it's coming from here and diverges. Okay, so converging lens makes light focus. This is how you can. Anybody ever burn insects when you were a kid with like a magnifying glass? Nobody did that? I didn't either. I knew some creepy kids that did. They're probably all in prison now. And then the diverging lens makes light go away, makes light unfocus. And what we want to do when we're drawing what's called a ray diagram is figure out where the image is going to form, where we're going to actually have the light focus itself. So let's put some focal points in here. Maybe we'll put a focal point here. And then we have another focal point on the opposite side that's the same distance away. So every lens has two focal points, one on the left side, one on the right side. Those focal points again, that's the distance from the lens to where the light focuses, and it's on both sides of the lens. Okay. And then let's draw an object, something that we're going to create an image of. So we typically draw that as a little arrow pointing up. That object has some size. We'll call this the height of the object. And that object is a distance away from the lens. We'll call this, oh, I don't know, let's call this DO. What do you think DO stands for? If HO is the height of the object, what's DO?
Distance of the object.
Distance of the object, from the lens to the object. Not rocket science. Maybe a little rocket science. And what we want to do is we want to know where is the image going to form for this little thing. So if I was using this to maybe project a movie or something, I could find out where I need to put a movie screen so that I can actually see this on a movie screen. Very useful, very practical kind of stuff. So there are two ways we can do this. We can either draw a picture that we use rulers and draw to scale, or we can calculate it. We can calculate it with this equation. 1 over DO plus 1 over DI equals 1 over F. So we know what all the variables are here except for one of them. What's DO?
Distance of the object.
Distance of the object. So from the lens to the object. What's F? Focal length from the lens to the focal point. What's DI then, do you think? We have an object, we're looking for where the image forms, so what is DI?
Distance of the image.
Distance of the image. So this will tell us where the image forms. I can run through and I can do the calculations, or I can draw it. The way I can draw it, I can draw 3 lines. And I can draw the same 3 lines for every kind of lens. The first lines is the easiest. The first line goes through the middle of the lens. We just draw a straight line. So let's draw that. Let's draw that in blue. So I'm going to draw a line that goes from my object, and I'm just going to go straight through the middle of the lens. Just a straight line. Can we all handle drawing a straight line? I suspect so. Not too complicated. Okay. The second line that we're going to draw goes parallel to the axis and then through or from the focal point. So we're doing a diverging lens now. We'll show you a converging lens on the whiteboard and do some measurements. So what I need to draw for my second line, I need to draw a line that's parallel to the axis. So I go from the top of the little arrow, and I just draw a line that's parallel to this optical axis. So just go straight in until I hit the lens. Just draw a line from the top, straight into the lens. And then the lens is where the funky stuff happens to the light. Right? There's nothing between the object and the lens, so the light doesn't do anything, it just goes straight in. But when it hits the lens, it's going to get bent. Now, this light, is it going to get bent towards this focal point or away from this focal point? Away. Why is it away? Because it's a diverging lens. So because it's going to diverge away, it's got to go off in some direction. It's got to go way up there. To figure out how it's going to go way up there, it's going to look like it comes from this focal point on the same side. So it's diverging away. To figure out how far it's diverging away, I draw a line from this focal point that goes straight. So let's draw that line. I'm going to draw a kind of little dotted line on this side that's going straight. And then when it hits this lens, that's where the light is actually going to go. It diverges away. Does that make sense? Now I see something here. I see green and blue are intersecting each other, aren't they? And the place where those two lines intersect, that's where my image is going to form. That's the image of whatever I'm making. So that will be DI. And the height of that is going to be HI. And you should have been measuring all of these things and seeing all these things in the lab. If you didn't do that this week, you'll do that next week. And then how many lines did I say you could draw? I said 3. How many lines have we drawn? 2. 2 lines are enough to get you where the image forms, but you can draw the third line to check. The third line is kind of the trickiest. Third line is a little bit weird. Goes to the focal point. And then goes parallel. So it's kind of the opposite of the second line. Right? The second line goes parallel and then through the focal point. The third line goes to the focal point and then goes parallel. Now with this picture, which focal point have we used already? The left one or the right one? We used the left one, so now we need to use the right one. We've got our object, so we need to draw a line that's going from the object and is going to aim to try to hit that focal point. So we just draw a straight line between those two. Okay? So let's draw our straight line. We'll do this in yellow. Make all of our eyes bleed. And we try to draw a straight line. Nothing happens to the light until we hit the lens. Then what happens when we hit the lens? I'm going to the focal point. And then where does it go? It's got to go parallel. So it's going to go out parallel to this. And here's where it gets another little tiny bit tricky. It goes out parallel. And then if I want to see where it intersects, I need to kind of imagine that this line would extend backwards. And where did it intersect? Same place. All 3 lines will intersect with each other. So that third line is a check on the other 2 lines. This can get very tricky. To get all these things to line up, you typically need to use a ruler and do very precise measuring. If you're kind of off a little bit, if you have shaky hands like I do, it might not all line up, but it should. So just imagine, pretend, if you're shaky. Okay, so this is how we can draw lens diagrams, ray diagrams. You can expect to be drawing ray diagrams on an exam and doing some measurements of them. Next exam will be in person. So what I've done is I've made up some worksheets that have a variety of lens diagrams that you'll be able to draw, so you can get some more practice. I would recommend going through homeworks and then actually going through and trying to solve these today in class. There is a drawer of rulers right over there. I will come and pass those all out. But before we do that, let's actually do an example on the whiteboard.